Okay, good. It's all sorted. Okay, so again, welcome everybody. It's Monsoon Seminar Series B. Thank you for joining us. We are joined today by Dr. Kana Yogashima from JAMS Tech. And so again, without further ado, please, if you have any questions, type them into the chat so we can see your question, and then I will call on you to read it out, or I can just ask it for you. Again, without further ado, Dr. Yogashima, will you please tell us a little bit about the East Asian monsoon and the westerly jet, please?
Thank you, Tara, and thank you also for Peter for inviting me to speak here this great monsoon series. So the title of my talk today is East Asian Summer Monsoon Westerly Jet Connection at Millennial Timescale. Here, I want to focus on the role of westerly jet on that East Asian summer monsoon seasonality, and a special focus on the millennial scale variation during the last glacial and also Holocene. Maybe all of you already know the Chinese cave record of stalagmite delta weighting record show millennial scale variation during the last glacial period, which show close similarity to the dance guard Oscar event. Together with such a Chinese cave record, similar East Asian summer monsoon variation in association with dance guard Oscar event were reported from Japan sea sediment. It's a color alternation between dark and light colors. As you can see, the Japan sea sediment shows repeated dark to light color alternations. According to Tada et al. 1999 and Tada 2004, they think that the grayscale of Japan sea sediment show variation in association with dance guard Oscar event with dark color corresponding to interstadials. This is one example of Japan sea sediment color, the lightness, to the upward showing the darker color of Japan sea sediment. You can see cross similarity between the Greenland delta weighting record of ice core and interstadial period. It's a warmer period of dance guard Oscar event, well corresponded to the darker color of Japan sea sediment. And you can see some time lag, but maybe this is not the real, but maybe due to the age uncertainty of Japan sea and ice core. So what caused such color changes? Tada et al. 1999 demonstrated that such color alternation is driven by East Asian summer monsoon precipitation changes. According to their hypothesis, the much precipitation over the drainage area of Yangtze River increased the river discharge, and then much more nutrient input to Japan Sea, which enhance the primary productivity there, and which generate suboxic to euxinic condition, and which organic rich condition makes that dark color deposition. So the switch between light and dark colors reflect the East Asian summer monsoon precipitation change. So the several proxies show dance guard Oscar event is also recorded in East Asian summer monsoon, and this suggesting that close connection between East Asia and North Atlantic at millennial timescale. However, that such dynamics and connecting mechanism is still not unsolved. So here we focus on the role of westerly jet. As you can see, westerly jet directly connect that East Asia and North Atlantic. westerly jet driven by that atmospheric temperature gradient between higher and lower latitude, and it's circled the globe along its meandering path at around 10-kilometer altitude. And westerly jet influence both climate change in East Asia and North Atlantic. In case of East Asia, the westerly jet path cause East Asian summer monsoon precipitation pattern. So westerly jet determines that monsoon rain band. So there is a close connection between westerly jet and East Asian summer monsoon. Over the North Atlantic, westerly jet path causes westerly jet transport heat and moisture from lower latitude to higher latitude. And also that sea ice expansion or the SST variation determines the position of westerly jet path. So the change of westerly jet may connect that climate change in over North Atlantic and East Asia. Based on this idea, here we try to find the evidence of millennial scale variation of the westerly jet path over East Asia. Before go to that, our reconstruction result, here I want to explain detail of the connection between westerly jet and East Asian summer monsoon. This is a figure from Chang and Sampe and Xie 2010. This shows that the westerly jet shown as a green arrow transport higher latitude transient weather disturbances from higher to lower latitude, and such disturbances met that warmer air from southern flank of Tibetan Plateau, which cause a convective condition along the westerly jet axis, that is a Mayu rain band. The point here is westerly jet to the north of Tibetan Plateau is important to maintain and cause that Mayu rain band. So that westerly jet is determines that East Asian summer monsoon precipitation pattern. So I think that relative position of the westerly jet to the Tibetan Plateau is very important to understand that westerly jet and East Asian summer monsoon coupling. Here I explain that seasonal change of westerly jet. To the upper figure shows a winter case. The left shows the temperature change, and right figure shows that westerly jet position relative to the Tibetan Plateau. During the winter, as I said before, that the westerly jet flow over the large surface temperature gradient. So winter case, that such larger temperature gradient is located to the south of Tibetan Plateau, so that westerly jet located to the south of Tibetan Plateau. But during late spring, that mid-latitude area become warmer, then that higher temperature gradient area shift to higher latitude, and that makes that westerly jet jump to the north of Tibetan Plateau. In summer, the westerly jet shift much higher latitude due to the warmer to the higher latitude. And Chang 2010, 2015 demonstrate that 4 steps of East Asian summer monsoon cycle accompanied with that northward shift of the westerly jet. So the first step is that jet located to the south of Tibetan Plateau, which causes that springtime precipitation centered around 27 degrees north. Then the westerly jet, before that northward jump, the precipitation area almost same, but that those areas expand a little bit lower latitude. Then after the jump of the westerly jet to the north of Tibetan Plateau, the Mayu rain band appear, and the northward higher latitude precipitation appear, and this precipitation zone shift much northward following the northward shift of the westerly jet. So there is such a cross coupling between the westerly jet and East Asian summer monsoon cyclicity. So based on this idea, I try to find the westerly jet change during the last glacial period. So we reconstruct past westerly jet changes based on that provenance study of Asian dust. In East Asia, there are two major dust sources. One is the Gobi Desert in southern Mongolia and northern China. The other is the Taklamakan Desert. During spring, when westerly jet locate to the south of Tibetan Plateau, the dust event is very frequently happen due to the cold air intrusion from Siberia. And during this period, dust from Gobi Desert, dust frequency at Gobi Desert is higher than Taklamakan Desert due to Gobi Desert located on the main pathway of cold air from Siberia. So that dust transport mainly from Gobi Desert suggests that longer southward position of the westerly jet. In contrast, during late spring to summer, westerly jet shift to the north of the Tibetan Plateau. Then cold air intrusion from Siberia decrease, and dust emission from Gobi Desert decrease. However, during the period, dust emission from Taklamakan Desert is still high because of the special topographic feature surrounded by high mountains. So the Taklamakan Desert causes a very convective condition even during summer, so that there is a high frequent dust event happen during summer. So the dust mainly from transported from Taklamakan Desert suggests that the westerly jet locate longer period to the north of Tibetan Plateau. Based on this idea, we reconstructed past westerly jet changes using Asian dust in Japan Sea sediment. We use two sediment core from southern part of Japan Sea. For the provenance study, we focused on quartz because quartz is the main component of Asian dust, and it's chemically resistant to alternation. So we use two parameters of quartz. One is the electron spin resonance intensity of U1 prime center. The other is the crystallinity. So ESR is a spectroscopic analysis to detect the unpaired electron within the magnetic field. In the quartz, there are several kinds of impurity replace silicon, and several kinds of defect. One of them is oxygen vacancy. Here we focus on the oxygen vacancy that is formed by the natural radiation. So that artificial irradiation, and after heating, such oxygen vacancy is converted to the E1 prime center, as I shown here. This can be measured, the amount of this can be measured by ESR. So the ESR intensity of E1 prime center represents the amount of oxygen vacancy. Since oxygen vacancy in quartz is accumulated during that geological time scale, there is a good correlation between that ESR intensity of E1 prime center and log-scaled age of mother rock. So ESR signal intensity of E1 prime center represent the age of mother rock. In contrast, quartz crystallinity represents that condition of quartz formation that is defined based on that powdered X-ray diffraction pattern of quartz. And it reflects the quartz formation condition. For example, if quartz formed under the high temperature or slow crystallization, such quartz shows that a higher crystallinity value. In contrast, the quartz formed under lower temperature or rapid crystallization, such quartz show a lower crystallinity value. So that advantage of this method is quartz ESR and crystallinity record different information. Combined these two parameters of quartz, we could know that source of dust. This is the data of Sun et al. 2013, and you can see this ESR versus crystallinity diagram. Those desert plot in different area. To check this method is useful for dust transported long distances. I check that dust fall sample collected in Japan. One sample plot here close to the Gobi Desert. Based on that model simulation using sprinters, that this event is mostly transported from dust is mostly transported from Gobi Desert, where very good consistent. The next dust fall sample is plot here close to Taklamakan Desert, and also model simulation shows that a dominant dust transport from Taklamakan Desert. So we have a confidence that even though Asian dust sample collected far from desert, we could know the provenance of such dust. So here I plot the result of Japan's sediment covering the last glacial period. And those, we measure the silt fraction of terrigenous material because silt fraction of Japan's sediment mainly reflects the Asian dust. So those samples plot here between Gobi Desert and Taklamakan Desert, suggesting that those Asian dust is transported a combination of both two sources. And interestingly, ESR value reflects that relative abundance between Gobi and Taklamakan Desert. So I will show you the temporal profile of ESR variation. This is a temporal profile of Japan's sediment. And second, to the upward, ESR value becomes smaller, suggesting that dominant dust supply from Taklamakan Desert, which could be interpreted earlier northward silt of the Westerly Jet. The second one is grain size of silt fraction. We interpret those this grain size change to the provenance change of Asian dust, because that Asian dust transported from Taklamakan Desert transport much longer distance compared to Gobi. So maybe such a desert samples show smaller grain sizes. And this figure shows that lightness of the Japanese sediment. And for comparison, the bottom one shows that Greenland ice core delta weighting record. The blue shade shows that stadial period, and also that light color Japan Sea sediment. And you can see that ESR intensity show millennial scale variations and with that dominant of Taklamakan Desert during interstadials, suggesting earlier northward shift of westerly jet. And the point here is Japan Sea record both East Asian summer monsoon intensity and westerly jet. So we could directly compare the two signals. And you can see that ESR intensity and lightness and also grain size shows that a very synchronous variation. For the further understanding of the westerly jet path and East Asian summer monsoon, here I show the diagram, histogram of ESR intensity during the period of Dansaka-Doshuga stadial and interstadial. You can see that stadial histogram shows that dominant dust supply from Gobi Desert, suggesting that a longer time stay to the south of Tibetan Plateau. And during that interstadial period, the ESR value suggests that between Taklamakan and Gobi Desert, suggesting that westerly jet earlier shift to the north of Tibetan Plateau. So we want to understand more detail based on the idea of Chang et al. 2015. They demonstrate the one cycle of East Asian summer monsoon and westerly jet like this wave, like this curve. And normal case that westerly jet shift to the northward following that. This black line shows the normal case, and they also show the case of earlier northward shift of the westerly jet that is shown this scenario A. And in contrast to a normal case, if that westerly jet shift later to the north of Tibetan Plateau, the scenario B, or the transition is not fully enough, the scenario C shows such a case. And here we want to know what scenario fit our results. The right figure shows the diagram of ESR value, and during that stadial period, the dominance of Gobi suggests this period is scenario B is a scenario C well fit, suggesting that westerly jet mostly stay to the south of Tibetan Plateau. In contrast, during interstadial, westerly jet shift to the north of Tibetan Plateau area, like this scenario B. So I want to know that such change of the westerly jet and East Asian summer monsoon seasonality cause what change of the precipitation and delta weighting value of precipitation. This is a result of Chang et al. 2015, where they show that like a scenario C case, it's similar to the case of in Dansaka-Doshuga stadial, prolonged spring condition. In that case, delta 18 precipitation over Chinese area show enriched delta weighting value. and the location of full cave, which value is close to 2 per mil, and that magnitude is very similar to the stalagmite delta weighting increase from interstadial to stadial. And interestingly, that the longer prolonged spring condition also cause a precipitation change, and precipitation decrease was observed over the Yangtze River drainage area. This may cause that smaller input of nutrient to Japan Sea and cause light layer deposition. So the westerly jet seasonal change could cause that delta weighting precipitation change and also precipitation change. To summarize this last glacial period, we reconstructed westerly jet path over East Asia, and which shows a millennial scale oscillation during the last glacial period in harmony with Danskad-Oshika events. The oscillations of the westerly jet seasonal northward progression largely contribute to the East Asian summer monsoon precipitation changes. So the question is why westerly jet seasonal northward progression change in association with Danskad-Oshika events? There are many possible explanations, but here I introduce one very simple one. That is the change of the surface temperature. This is a result of water housing experiment. And you can see that very cold condition, not only at higher latitude, but it's expanded to the mid latitude. Such a cold temperature prevents the northward jump of the westerly jet and maybe cause a prolonged spring condition. Okay, so I want to move that Holocene part. The question is whether there is a similar westerly jet East Asian summer monsoon coupling during the interglacial period. If there is, we could examine the detailed coupling system between the between the westerly jet axis and East Asian summer monsoon spatial precipitation pattern. So again, here I show that ESR versus crystallinity diagram and sample of Japan Sea covering the last 12 kilo-year plot here, also between the Mongolian Gobi and Taklamakan Desert, and ESR value shows the relative abundance from the two deserts. This is a temporal profile of ESR variation. And you can see that several millennial to multi-millennial oscillation during the Holocene, like this. So I want to compare such millennial scale variation of the westerly jet during Holocene to the spatial precipitation pattern of East Asian summer monsoon area. This is the same figure, and the yellow shade shows that earlier northward shift of the westerly jet period. And you can see that precipitation increase of the almost northwestern limit of the East Asian summer monsoon precipitation, East Asian summer monsoon region. However, that lower latitudes show negative relation, and those northward position of the westerly jet is show the drier condition, and much lower latitudes show no clear relation to the ESR value. So we could suppose that the area northward shift of the westerly jet generate much precipitation at the northwestern limit of East Asian summer monsoon region. To test this hypothesis, we compare the much more record dividing those 5 periods. This is the result, and we choose 18 precipitation record from China with a precise age model. And we separate each, we classified each station into wetter, drier, or intermediate condition. And the wetter condition area is shown as a purple shade. And you can see that the wetter condition area shift from north to south and north in accordance with that westerly jet change of westerly jet path changes. So this figure also shows that the precipitation pattern of East Asian summer monsoon region is well responding to that seasonal northward shift of the westerly jet, even Holocene period. Then I also checked that this figure and try to fit the scenario based on that ESR value during Holocene period. And during the period when westerly jet shift to the area shift to the north of Tibetan Plateau, the most samples, most dust is shows that ESR value correspond to Taklamakan Desert, which means that the area northward shift of the westerly jet, and other period shows that later northward shift of the westerly jet. So it's like a shift between the scenario A and B. So the still remaining question is what caused such millennial scale oscillation during the Holocene? I have no clear evidence yet, but it is too speculative now, but I suppose that solar activity change may likely cause such millennial scale westerly jet change during the Holocene. This figure shows that wavelet analysis result of solar activity, and those area northward shift of the westerly jet happen together with that very intense cyclicity period of decadal to centennial cyclicity. So there should be some connection between that solar activity. For example, that solar activity easily change that stratospheric circulation pattern, then which could be propagated to downward to troposphere circulation, including westerly jet path. So I want to examine this possibility further in the future work. So summarize the Holocene part. The reconstructed westerly jet path during Holocene shows millennial scale variations, which seems to determine East Asian summer monsoon seasonal cycle, generating precipitation such as northwest to southeast contrast within that monsoon region. During Holocene, westerly jet East Asian summer monsoon seasonal cycle oscillate between scenario A and B. That is a little bit different from the oscillation during glacial period. That during the glacial period, maybe that oscillate between scenario B and C. So the result of our study shows that the less precipitation around Yangtze River Basin happened during that Dansagat-Oshuga studial period. So that scenario C is very, so that Yangtze River or Full Cave area is very sensitive to that oscillation between scenario C and B. But in contrast, during the Holocene, the oscillation between scenario B and A is more sensitive to the precipitation of much higher latitude area. Okay, that's all. Thank you for your attention.
Thank you very much. We'll let everybody have a moment to type their questions into the chat. I did have one short question before people type in their others, is so I know that your record is from about the last 60,000 years to present, and it does appear that there's a long-term trend that exists in the data set, because you have the millennial scale variability that's superimposed on what looks like a longer term, like maybe orbital scale trend. Is that related to any type of long-term drying, or I don't know if there are any other types of like feedbacks, I guess, that you had looked into there? Because I guess I'm thinking about like long-term drying and maybe desert expansion type of feedback. So I was just curious if you had looked into that. Sorry, it's a bit of a rambling question. But.
Yeah, thank you for your question. It's a very important part. And there is also a orbital scale variation of the Westerly Jet path. But first, I think it's very closely related to that insolation change. But there is several exceptions. For example, exception is the Holocene period. And so now I think that situation is not so simple, but maybe the insulation should be influenced with Westerly Jet path, but not only insulation, but also some change. And I think it might be that ice sheet size, which change that Rossby wave and the Westerly Jet position. So both the combination of orbital insulation change and also that ice sheet size controls that Westerly Jet position for longer time scale. And the Westerly Jet and East Asian summer monsoon coupling is not so clear during that longer time scale. So I think it's very interesting, but not now I cannot clearly explain that the decoupling and coupling.
Yeah, I agree completely. It's beautifully complicated, and I think it keeps many of us busy. And so, but I really like your record here. It's been a while since I've seen such a fine-tuned Holocene record, and I'm less familiar with the electron spin resonance, and so I think that's a really cool method. And especially what you can figure out with the interaction. Yeah, so does anybody else have any burning questions here? Surely. Okay. Oh, here we go. We have one. Okay. So the person asking this question is Shuichao Wu. I apologize if I mispronounced your name. And they have asked that I read it out. So they say, thank you for your presentation. I have a small question. As your reference also, according to Sun et al. 2013, the ESR and chlorine also affect by grain size, same provenance, but different signals. So is there a possibility that these variations just induced by grain size changes from a stable source, so like Gobi Desert, rather than different sources? Good question.
Yeah, good question. But grain size change, which I show this slide, is only 1 micrometer. That is very small compared to the Silt's paper. They show that ESR variation between different grain size fraction, but Japan sea dust variation is very small compared to the Silt showing grain size influence. So I think that the grain size shift of Japan sea is very small to influence that. I'm sorry. Yeah, it's better to show my slide. Maybe here. Okay, those variations are very small, so that not affect that ESR signal from each desert. So I think that grain size change could not explain that ESR, these large variations.
Okay. Does anybody else have any questions for Dr. Nagashima? Well, I guess that's it for questions. So I would ask that everybody put their hands together again for this nice presentation given today by Dr. Kana Yogashima. And so before you all run away, I just want to remind you that in, I think, 2 weeks, we have another monsoon seminar on the 30th of March by Dr. Xiaoli Zhao. And so I just want to also remind anybody who's watching a recording of this that over the next few weeks, we'll also be having several daylight savings time changes between, I think, the UK and the US and Australia, who often change their times. Just so keep on your toes a little bit with the times, and we'll try to keep everything updated as needed. But otherwise, I hope everybody has a very nice evening, afternoon, or morning, wherever you are. And I will see you very soon in a couple of weeks. Sorry. Thank you very much.
See you.
Bye.